Morning everyone. I choose to believe the dwindling attendance after yesterday is due to this being the last day of the conference and the social last night. Thank you to those of you who are here. It's not a comment on the two keynotes we've got this morning. So my name's Nick Horn. I run the engineering team at ARM, and I'm going to talk to you about what we've been doing in the ARM architecture to accelerate ML and how we're enabling that in the ecosystem. So 6 years ago, my former boss, Jem Davis, some of you will know him, stood on the stage at Linaro Connect and talked about how we were enabling machine learning to explode with open standards and collaboration. I think we can probably agree that there has been an explosion in that period, and ARM's been part of that. 6 years ago, the ML group was relatively small in ARM. It was off in a corner, not that well loved. It's quite different now. We're in a lot of demand. There are loads of stuff we're trying to do. We're trying to move really quickly, and it's a very exciting world we're in now. I don't have my notes on the screen down there. I'll carry on, but if you could fix that, brilliant, thank you. Okay, so I wanted to reflect a bit on there's an academic theory about how the human brain develops. Windows of brain plasticity and brain development. And there are some different phases academics talk about, and they actually map quite well to the ML world. So the first stage is a sensory stage. Babies are learning about the world around them, recognizing their parents, their first words. Then moving into developing motor, language skills in their kind of early years, and then through to higher cognition. I haven't looked at all of Jem's slides from 6 years ago, but I bet they had cats in them. Other animals were available at the time, but kittens were cuter, and Jem was a cats person, so they were almost certainly there. That was what we were talking about, differentiating different types of animals, recognizing faces, recognizing where things were in frames. So that was very much the sensory phase of machine learning development. Today, we've obviously all heard about Llama. Llama 2, it's even out of date now, it's Llama 3. This is all about developing language, and there's also a lot of advancement in developing motor skills, self-driving cars, robotics. So it's very much where we are now. What does the future hold for that higher cognition phase? And I think that's very hard to predict. If I'm stood here in 5 or 6 years' time, or my successor is, what are they going to be talking about? I don't think Jem would have predicted where we are now with the explosion of generative AI, and I think it's therefore very hard to predict that future. And that's going to tell us something about the platforms that we need to be developing into the market today. So that higher cognition phase, that's all about real deep understanding. LLMs, despite their impressive performance, they don't have deep understanding of what's going on. They don't have those higher level executive functions that we as humans are developing through our lives. In fact, that process never stops. Okay, so we have a few tenets that we developed a few years ago within my team. And the technology team in ARM that are guiding how we prioritize and how we think about what we invest in ML at ARM. And I'll just run through them. And whilst we wrote them a few years ago, they very much still hold true and in fact becoming more and more validated. So we believe that ML will replace most classic heuristic algorithms. We're seeing a lot of applications where they're mixing classical CV processing at the front end of a pipeline, moving into an ML pipeline, and then moving back maybe into some classic algorithms. Over time, we're replacing more and more of those classic algorithms as researchers come up with more efficient ways of doing the work at better quality, lower power, whatever the metric is in using ML. So ARM's hardware and software needs to adapt to that world and keep advancing the performance of ML. New types of network will continue to emerge. If you look at graphs of numbers of papers published in the ML field, it's a hockey stick. It's growing exponentially. Researchers will be inventing new stuff all the time. The last major thing was transformer networks, They've been around a while, but they've really come of age in the last few years, and they're what's driving a lot of the generative AI advancements. So we need solutions that will be future-proof. Our hardware sits out in the field for a few years if it's a mobile phone, way longer if it's a car or an industrial IoT device. Demand for compute is insatiable, will continue to be insatiable. We need to be investing in platforms that are ever more performant, area efficient and power efficient. Standardization, it's still the Wild West out there in the ML space. There are loads of frameworks, they come and go, they change in popularity. People are trying to coalesce around particular frameworks. PyTorch is the place to be at the moment. And on the standardization front, ARM has something called TOSA, TOSA Operator Set Architecture. So this is an attempt to define a future-proof set of low-level operators that we can map networks to and very accurately define their behavior, so you can design hardware to them and have confidence that hardware, the models will run with the same accuracy on any hardware that is compliant. And then lastly, a vibrant ecosystem. There's a huge ML ecosystem out there. It's moving really quickly. We need to make sure everything we do gets plugged into that ecosystem. All of our libraries are enabled through that ecosystem so that everybody can get the best out of our hardware. Okay, so a bit about the different types of places that you can run machine learning. And there's very much a horses for courses thing going on here. You can run ML on the CPU, really flexible, first choice for developers, quick to deploy, modest performance, but still very good performance at a few tops, so teraops per second. And then the other end of the spectrum, you've got NPUs. You're not going to beat an NPU for performance density, and that's great for the really massive models that you need to run really quickly. But if anyone here has worked with NPUs, they tend to be they've got their quirks. You have to do a lot more work to target your network to those NPUs. It's worth it for the very biggest networks, but it's nothing like a CPU in terms of getting stuff running quickly. And for the smaller models, that makes a lot of sense. And then GPU is somewhere in the middle. GPU is probably of the ARM IP that's out in the world where most ML is being run, particularly on mid-range smartphones. They've all got GPUs. They don't have NPUs. They can't afford the area. So loads of ML is going on GPUs. And it sits somewhere in the middle in terms of that performance flexibility scale. And just a bit of data to back up what I've been saying. We took a load of networks. They're ranked in terms of network size, essentially. We've benchmarked them on 3 different pieces of IP in real silicon, doing an apples for apples comparison. And you can see that with small networks, the CPU comes out on top. It's simply not worth the overhead of moving your data onto the NPU or the GPU, starting that up, because the workload is relatively small, so just do it on the CPU. At the right-hand side, NPUs coming out on top because it is worth moving the work there. You get the benefit of the acceleration for those biggest networks where the developers are prepared to put in the effort to target the NPU. And in the middle, it varies. Sometimes each piece of IP is better. So we see that actually for small and medium networks, the CPU is a really good choice for porting networks too, and we've been working hard to make sure that we can get the best performance out of the CPU for those sizes of networks. So onto the ARM architecture. So this is showing a lot of history of the ARM architecture, and I wanted to talk from sort of V7 onwards, where we can really see some ML acceleration extensions coming in that have really got us to where we are today. So in ARM v7, Neon was announced in about 2006. So Neon, the sort of the big SIMD extension. It's in terms of CPU technology, it's what loads and loads of ML is running on today. In those mid-range phones, alongside the GPU, we're running on the CPU on SIMD as well. And then ARM v8 the architecture was announced in 2011 with some point extensions announced in the years after that as things in the ML world came along that would benefit from further acceleration. So SVE was announced in 2016, and then a bit after that, bfloat. So bfloat is a 16-bit floating point format that allows really easy quantization from the native 32-bit where a lot of models are being trained. And we put in some dot products extensions, and some of those were rushed through the architecture really quite quickly to respond to the moving ML landscape. And then we come on to ARM v9. So SVE2 was announced in 2019, so wider vector widths. And then we announced the big step forward here, which is SME, got announced in 2021. And I'm going to come on to talk in more detail about SME because that's a step change in performance. So you can see lots of machine learning focused acceleration going into the CPU over that last decade and a half really. It's worth the other note that the other thing that's going into the architecture is security, and I think those two areas will continue to be the focus for how we take the architecture forward. So the bars aren't coming out very well at all, oh dear. Actually, they're coming out better on your screen, good. So this is putting some numbers behind what I just talked about. So the techniques that have come into the architecture up to V8, the primary ones are shown in that diagram. There's also, so that I didn't mention, some limited matrix multiply capability went into V8. And that's taken us from 8-bit max per cycle up to 64 8-bit max per cycle over that period. And that's actually, that's pretty decent. That's almost an order of magnitude. Then we bring in SME, and we're getting a massive leap forward. So SME will deliver up to 1024 max per cycle, 8-bit max per cycle, depending on the implementation. And that's done through the addition of this matrix engine with a lot of matrix tile storage. And it's all about changing the ratio of the number of loads you need to do to compute cycles. So back in V8, we'd got to, with the limited matrix multiply capability, we'd got to 1-to-1 ratio of compute cycles to load cycles. To get to, once we implement SME, we can get up to 256-to-1, so a massive change in that ratio of compute operations you can perform per load cycle, per memory load cycle. That's enabled through that tile storage. It's enabled through the way the matrix engine works. It uses something called outer product computation. Google it, look up the maths, but it's a very efficient way of reusing the data that you load and not having to reload as you traverse these matrices and tensors to do the element-wise operations that you need to. Okay, so use cases, loads, and these are the ones that we can imagine today. And these are the ones that we're working on, making sure that we enable well through our stacks and our examples. But I think a key point here is that these won't be the use cases that are running on the phones that deploy, the phones that are being designed today when they deploy, and certainly not the ones that they'll run over their lifetime. Things will continue to evolve. But particularly in mobile, we're seeing this is the baseline of this. This will be table stakes. Phones will need to be able to run these on device, on the phones of tomorrow. They'll be mandatory. What we are seeing in handsets is that, in particular, is that people are putting in hardware acceleration blocks to accelerate particular networks, and that's all very well, but there's a high danger that that hardware will become obsolete quickly as the world invents new networks, new techniques, new use cases. So we believe that actually that combination of put in that acceleration, but make sure you've got a really, really performant CPU in there with the latest technology, such that you've got more flexibility to adapt to those future use cases. So I wanted to dive a bit more into large language models. They're obviously the thing at the moment. Everybody's talking about them. New ones are being announced a pretty much daily basis. So it's worth understanding a bit more about how they run and therefore what you need to optimize and worry about. So two phases. There's a first encode phase. So this is taking the question you input and extracting the relevant information from it. This phase is compute bound, and it affects the time for the first word of the answer to come out of the model. The second phase is decoder phase. This gets run repetitively per token of the output, so per word that's coming out of the output. This phase is pretty much going through the whole set of model weights and activations, so it's memory bound. And this affects the times for each subsequent word coming out. Stating the obvious, these models are huge. 8 billion is a medium-sized model. But it's the kind of model that people are talking about running on your phone. Clearly that's pushing the limits of memory capacity in today's phones. And so what do we do with this this information in terms of how we optimize the platform? So to get the first token out more quickly, you need more max per core, and you need dedicated hardware instructions to deal with any funky data types that are being used. And to really work on that ISA to accelerate the kinds of operations that need to happen in that phase. And then the second phase, obviously the chip and phone designer needs to do the best he can in terms of memory bandwidth and interconnect bandwidth for getting data into the CPU. But then you need to look to software to achieve better data compression. For something like llama.cpp, so llama.cpp is a lightweight runtime built around Meta's Llama model. There are 20 different compression techniques in there. Those have been tuned to trade off speed and accuracy through the model, and it turns out that different techniques actually work best with that trade-off space, different layers of the model. Hence, they've got to 20. Two fairly simple ones are shown in the diagram of whether you quantize down to 4-bit per channel or per block. The point here is that software is key to keeping pace and being flexible, such that when the world invents a new technique, when the research around 1.5-bit quantization turns out to be deployable, then we need to be flexible in getting that to run on today's devices with these mixed data types. Okay, so you're now all watching the video on the left. You probably can't read it, but you can probably see the pace at which, the speed at which answers are coming up. So this is a demo running on real hardware that some people in my team did. It's running Llama 3, so the model that was announced or released to the public 2-3 weeks ago. And this is running on a Xiaomi phone, so this is without SME. Today's phone, really decent interaction rate achievable on today's hardware. And as I said, this is running Llama 3, so within kind of about 48 hours of Llama 3 being made public, we had plugged in our optimized kernels underneath, and we'd achieved some pretty big performance improvements in getting our software underneath the native release model. In the encode phase, we went up to about up by about 64% through mapping efficiently to the vector acceleration in the core, and then the decode phase through compression techniques, through reducing bandwidth, through using int4 mainly, achieved 25 to 30% increase on both Llama 3 and Phi 3, which is Microsoft model that was announced a few days after Llama 3. So I think that demonstrated how quick it was to get optimum performance on CPU because of that flexibility. Okay, so a bit about how we plan to enable developers to get the best out of the platforms. I do say to my team sometimes they don't necessarily like it, that actually I don't care whose software a developer uses, so long as they can access the true performance potential that the CPU's provided, and that they can do it in a timely manner, and that they can get updates as the world invents new data types, as people invent new optimizations. Whilst in theory anybody could do that, in practice actually only ARM can do it today, because we've got the advanced knowledge of that architecture. We've got a team dedicated to squeezing the best performance out of there. So our strategy is to develop these highly optimized kernels, deliver them, open source them. We want people to integrate to those libraries. You are free to cut and paste the code and pull them into other frameworks, but then you don't get the benefits of when we put in a new optimization or fix issues when they come up. I've mentioned Google's XNM pack on there. It's an important part of our strategy. It's an important library that's out there. It's the default CPU backend for TensorFlow Lite and for PyExecuTorch. So we're working with the XNM pack team to get our optimizations, the kind of optimizations we saw on the previous page for Llama, into that library, so that developers can get really low friction access to those optimizations and continue to take the benefit of them. We're also working with a lot of the other frameworks on this slide in order to get those, in order to do the same thing, get them to integrate to our libraries. We have to go broad, because there is a lot of sort of one-to-one linking of the third-party application space to the runtime. People pick their favorites. Sometimes they're within vertically integrated companies, so Meta and Google are all deploying on their own runtimes, and the same for many of the Chinese players. So we need to be rolling up our sleeves and working closely with all of them to get the ARM low-level libraries underneath. And a bit more about software enablement. So we're working in lots of different areas. We're enabling through some foundational software, so compilers, kernels. We've got the work in my team around libraries and our own runtime RMNN, and integration into, as I was talking about, many of the important runtimes that are out there. We've been working in specific ML compilation open source projects. So we've been contributors to TVM, and we're very active in MLIR right now. And then I touched on kind of CV earlier, but there are some CV related projects, Halide, a high level CV language, an OpenCV low level library project. Important because of the adjacency. Many applications are combining ML and CV, and that actually comes back to SME. It's really good at CV as well as ML, so it's actually really easy to combine those workloads and run them together and be able to do that migration over time from those classic CV algorithms to ML algorithms. And then we've got a lot of work about benchmarking of all the important workloads that matter, and making sure that we're able to get performance out of all of those different frameworks, and we're not seeing different experiences across all the different frameworks. Okay, so the thought I wanted to leave you with is that we've been delivering through that sort of couple of decades of innovation in the architecture and all the enablement, that we're unlocking a lot of potential value through running ML on the CPU, and that they're really coming of age right now. So thank you for your time this morning.